Okay, let's start. So last time we were discussing perspective function. Okay. Yeah. Sorry for that. And now let's continue. And next topic is conjugate function. This is an important concept that we will be using in the lectures later. But now we will just see what it is. Yes. So conjugate function. Um, let's say, yeah, consider a function f of x. Okay, it can be convex or non-convex. Okay, and conjugate function of that function f of x is denoted as f star y. How do you define that? It is, you first draw a line through origin by transpose x, and then take the distance. It's not distance. Subtract this. Subtract the function from that line. Okay, and then for all x belonging to the domain of the function f, which is the maximum, that is the conjugate function. So don't worry, we will explain. Let's say we have a function f of x. Okay, so what is the conjugate function of f of x evaluated at a particular point y? Okay, for that you have to draw a line through origin with slope y. So here I am explaining with a case in R. Okay, one-dimensional case. So first we have the function here, and then draw a line with slope y. That will be having the formula xy, right? A line through origin with slope y, that is xy. So that is this part. This is the line through origin here. And now what you have to do is, now just observe the difference between this line and the original function at all x. Okay, see the difference. So and find at which point it is giving maximum difference. So here, so one important fact is you are subtracting the line from the function. Sorry, you are subtracting the function from the line, right? So at this point, what will be the difference? You have the line and the function, both are coinciding, so it's 0. At this point, it is this difference. At this point, it is this difference. But if you consider this point here, a negative x value, here you are subtracting from this point to this point. Okay, so that this term will be negative that point. Okay, so we are, it is not, my point is, it's not just the distance, the absolute value, the sign is important here. Okay, from the line you are subtracting. So maybe for this case, if you consider a point here, so yeah, what is the maximum distance here between this line and this function? So here it is this one. Okay, so then uh, at this point we have this distance, so that is the supremum value of the function. Let's take another example, more easy. So we can have a graphical interpretation. So let's consider a simple function f of x equal to ax minus b. Okay, so first before going to graphical interpretation, let's see how we can evaluate. So we know the formula f star y equal to yx minus ax minus b. Okay, so in this case, so I just rearrange this and we have y minus ax plus b. So what will be the supremum value of this? So you know that when y equal to a, this term will be 0, right? In that case, it's a constant b. So supremum value or maximum will be b itself. Okay. If y is not equal to a, then here we have some y minus a and x term, right? X term is there. So then you have something like x plus b or cx plus b. What will be the supremum value of this? So x can be anything, right? X belongs to R. So then the maximum value will be infinity, right? So that's what I write here. I wrote here infinity. So when y equal to a, it is b. When y not equal to a, it is infinity. Now, how can we see this graphically? Let's take this function. So we have this function here. Okay. So now what we have to do is draw a line through origin. Okay. So this is not, we have to draw. Okay. So when the slope of the function. So now what we are going to do is examine this distance between these two lines for different slopes, right? Here I'm drawing a line with slope equal to, what will be the slope of this line? Yeah, right? Because this line is parallel to this line, which is having a formula ax minus b, so the slope is a. So I'm drawing a second line ax through origin, right? So this will also have a slope a. So what will be the distance between this? B. Right? So maximum distance will be b, right? Or the distance is constant here. Even if you take any point, the distance will be constant here, which is this point, this distance, which is b. So whenever we the slope is a, y equal to a, the value of the conjugate function is b. Okay. Now what happens if we slightly change the slope? I draw a line like this. What will be the conjugate function? So let's so this slope is less than a, right? So we are at some point here. Okay. So what will be the value of the conjugate function? That the value is maximum difference between, you subtract this red line, the function, from this orange line, right? So here, so at this point it is negative, right? Towards this side it is negative because the line through origin lies below the red line or original function. But you have to go to the point where that distance is maximum. So you can see that as you move to right, here the distance is this, but if you keep on moving to left, the distance increases, and finally that is infinity. So you have infinity here. Okay, sorry. Let's say this is the infinity. So you have infinity here. Okay, and even if you consider a point to the right, that will be infinity. Any function, for example, if you draw something like this, again you will see that the distance is increasing here, and that will be infinity. So the function has uh, we have this conjugate function. The conjugate function of ax minus b is a when the slope y equal to a. Sorry, it is b when the slope when y equal to a, and in all other point we have infinity. Okay. It's something like this. Okay. So yeah, let's take another example. So you may wonder why this is important, but this is an important concept that we will see later. We will just mention an important aspect here now, but in later in coming lecture, this concept is very much used. So this is like we use the word conjugate in many scenarios, right? So here we are saying we are forming the conjugate of a function. Like we know what is the conjugate of a complex number, maybe, right? Or a matrix. We know what it is. Here it's a conjugate of a function. So let's take another example. We have the absolute value function here. So what will be the conjugate of that? So first we draw a line with the slope +1. Okay. So that will be this line here. So what will be the what will be f star y in this case? So it is the maximum distance from this line to our original function. So if you consider all the point to this side, that will be it will be minus infinity, the maximum value, right? Because the sign is important. This part is below the function, so that will be minus infinity. So you can discard all this point because that is going to be minus infinity. But all point towards the positive x, it is having a zero value. So it will be zero at this point. Okay. And if you take any line other than this, for example, this guy here. So what is the slope? It is less than 1, right? This was having a slope 1, this line. Now we are considering another line which is having a slope less than 1. So let's say this point here. Okay. In that case, what will be the value? That will be
also minus infinity. It's zero or infinity. But on the definition it says.
So we have to subtract this guy from the function and see the maximum distance, right? Or difference. What will be this case? So see here, this line is, sorry, this line is below our original function at all point apart from the origin, right? So that at origin that will be 0, right? So that in this case it will be 0. 0 is the maximum. So again we have yeah, here we have 0 point. So you can see that like even if you consider a line with a -1 slope, okay, again the maximum difference will be at the origin, which is 0. So at all the points between -1 and +1, it is 0. But if you take any point greater than if you consider any line having a slope greater than 1, for example, this guy over here, what is the difference, maximum difference? It is infinity, right? We can see. So this distance is increasing and it's going up to infinity, right? But towards the left, this is negative, right? So if it's minus, we don't need to consider here because we have positive value. So that will be infinity. So in this case, our conjugate function will have a form like this. This is infinity. Okay. Let's see what is this line. Yeah, this is also something like some point here over here. That will also have infinite value, right? So so this is the conjugate function of the absolute value function. So we had an absolute value function like this. Now the conjugate is this guy. Okay. So we saw two examples here.
The line you just draw, that is between in the conjugate function. It's between 0 and -1.
One second. Which was the line that I just wrote?
The
I should have
last green one that you added. That one.
this one.
Yeah, that one is within the interval -1 + 1.
Yes, it's yeah. Sorry.
So
Yeah,
it's not.
I said infinity, right?
Yeah, you drew
So
it on the left
yeah,
side of the
that
line.
is wrong. This is
Yeah.
having. So I thought it is something like this. It's not.
Then it's
So this is having a slope between maybe here, right? Somewhere here. So yeah, of course, this is lying below our absolute value function at all point except origin. So that will be having
there is
0 as the conjugate value. Okay, sorry. So this is the shape of a conjugate function of absolute value function. Yeah, so we saw two examples. So this is how conjugate function is. This is a graphical interpretation, and we can just sometimes if the function is differentiable, or if you have a way to find the minimum value, or sorry, a maximum value or supremum, we can do stuffs like this. So the important thing is, if you see f star, so f star is a function of which variable y, right? So you can see that f star is convex no matter what is f of x, irrespective of f can be convex or non-convex, but f star will be convex. Why? Because if you see this, so now what we are investigating is, what we are checking is whether this function is convex in variable y, not x, right? Because this is a function in y. So in that case, this is what? This is just an affine function, right? In y, right? Y transpose x minus f of x. So in variable y, this is an affine function. Then like this is taking the supremum of such affine functions, which will be uh, convex. So that this is the important point. F star will be convex even if f uh, is not. Okay. So conjugate function of a non-convex function will also be conjugate. Now some other example, minus log x. Okay, minus log x is a convex function. Uh, so what we are investigating is f star y. What is f star y? So just plug the formula. Just use the formula. It is supremum of xy minus log x, which is xy plus log x. Now, just to find the maximum of this, just when the function is differentiable, we can find the maximum by differentiating, right? So let's call this guy as g of x. So g dash x is y plus 1 at x star. This will give maximum value, which I am equating to 0. Okay. Then x star will be minus 1 by y. Just plug that, then you will get this guy when y is less than 0. When y is greater than 0, you cannot apply this formula because this is not defined. In that case, you have to see. So for example, so this is our log x. This is our log x, and what will be, so I am considering a value y here. What is y here? Maybe 1 plus 1, right? The y is the slope of this line, so plus 1. So what will be the maximum distance? It will be infinity, right? So yeah, so this distance is increasing and it will be infinity. So in that case, it will be infinity. Okay, so this is the conjugate function of minus log x. Another function, this is interesting, a quadratic function here. Okay, with q in positive definite, strictly convex quadratic function. Why do you use the word strictly convex? Because q is now not in q is not a positive semi-definite, it is positive definite function. It has all the eigenvalue positive. Okay, So why do you, so if you see, okay, so there is one point, we use a half here. Any idea why do we use a half? Often in a quadratic term, we use a half because in many calculation, it gives a nice expression later. For example, mm, if you differentiate twice, what will be the value? Q, right? So then that there will be a 2 coming out of differentiation. That 2 and this half will get cancelled. So to make everything convenient, we use a half of in quadratic form. But even if this is not there, that doesn't make any difference. Okay. Yeah. So we have this quadratic term, and now we have to find the conjugate function of this quadratic function. So this is our original formula, y transpose x minus our function of x. So let's call this guy as g, g of x. So to find the maximum, I'm taking the derivative and equating that to 0, right? So when I take the derivative and equate to 0, I get y minus q x star. So am I correct? Just see. So y minus q x star. Now I have x star equal to q inverse y. Just plug that here, and then there is some minor adjustment, like you have to use q minus inverse transfer. So q is already a positive definite, so it's a symmetric matrix, right? So then if you take, then the inverse also will be symmetric. And if you take transpose of that, that will be the same guy itself, Q inverse. So now after some rearrangement, you will get the function like this. So yeah, so the point is we had a function like this, and the conjugate of this quadratic function is this guy. Just replace Q with a Q inverse. Okay. Yeah, that's a conjugate function. Yeah, so we will be using that in coming chapters. Now, another question is, so usually when we have, for example, if you take a complex number and you define a conjugate, so there, what will be the conjugate of a conjugate? For example, 1 plus 2i. Conjugate will be 1 minus 2i. Again, if you take the conjugate, 1 plus 2i. So often in literature, commonly, when we take conjugate of a conjugate, we will get the original thing back, right? So now we will see what is conjugate of conjugate of functions. So it turns out to be an interesting thing. It is not original function here in all cases. Okay, so let's say we have a function like this. Okay, and if you take the conjugate and the conjugate again, actually what we will be getting is this guy here. Okay, so that is can you say what it is?
The convex value.
Yes, but here there is no set, right? I just said about the function, right? So function doesn't have a converse hull is a concept for set, right?
Yep.
Okay, so here what you said is correct, but then in that case you have to consider this set, form this set, and then take the converse hull of this. Okay, yep. So what is this set? It is the epigraph of the function, right? Yep. Okay, so you take the epigraph, then take the converse hull. Yep. Okay, then you get a function. Then you will get a new set, and the function corresponding to that new epigraph will be the conjugate of a conjugate. Okay, so in other words, this is simply called a convex envelope. So we have a function like this, which is non-convex, and the convex envelope is like you just draw something very tight, which makes it convex. Now this function is convex, right? So that is called convex envelope. So if you take conjugate of conjugate, you will get convex envelope. So F double star is the convex envelope of F. How do you formally say that? What is F envelope, convex envelope? Epigraph of F envelope, okay, is convex hollow epigraph of F. That's what we just saw. So we have this function. So epigraph of that function will be this region, okay. And now you take the convex hull of that. So that will be this guy, and so that the function corresponding to that convex hull will be convex envelope. So this is an interesting concept here. We are not going into detail. We just mentioned this property and pass on. Then, yeah. But what happened when the function is convex? Then the function is convex. Then you are taking conjugate of conjugate. Then you will get what will be the convex envelope of a convex function? It will be the same function, right? So if f is convex, then in that case only, if you take a double conjugate, you will get the original function back. Yeah. So there is some technical condition. F should be closed, but we are not going to detail of this boundary condition. Let's skip that. But the important thing is, yeah. So you will get a convex envelope of that. If the original function is a convex function, then the double conjugate will give you back the original function. Yes, so that's what the concept of conjugate function. Let's move. Yeah, so next topic is quasi-convex function. So this is something interesting. So let's check this function, this guy over here. Is this function convex? Why? Because if you take 2 points here and draw a line that is below the function, right? So in that case, this is not convex. But when you see this function, though this is not convex, you may get a feel that you can minimize this, right? Because this is not something like this form. This is not convex, right? If you take any 2 points, draw a line that is falling below the graph. But again, when you see this function, you will like it because you feel that, okay, this is not convex, but this is something similar to convex. I can minimize this, right? So this sort of function is falls under the category quasi-convex. So now we will see what it is, how we can define. So function R into R is quasi-convex if first thing is domain of f has to be convex. Otherwise, there is no point, right? The domain has to be convex. And the sublevel set. So we saw what is a sublevel set. How do you form a sublevel set? For example, for this guy, an alpha sublevel set is, so we have the axis here. So consider alpha here, take this point and find the domain where this function is having less than alpha value. So all these points of x, the function takes value less than alpha. So this is alpha sublevel set of this particular function, right? So, uh, for a function to be quasi-convex, first we consider alpha sublevel set, okay? Then that set has to be convex for all alpha. For example, here we have this function, okay? Let's see what is, so let's take a point beta here. So what will be beta here? Alpha beta sublevel set here. Minus infinity to, yeah, C. I think it's C. Yeah, C. So from this point, right? you find so this is beta, so you find the corresponding argument value at, right, it is c, and then all this point to the left. So that will be minus infinity to c. So what will be alpha sublevel set here? It will be a to b. Now, for example, I'm drawing in different thing, gamma. What will be is gamma?
Yeah,
It's a null set. You cannot say zero because it is a set. So if there is no element in that set, it is a null set. If you say zero means when that set has one element which is zero, that's different. Okay, so null set. So now what I'm saying is, no matter what is the value, whether this is alpha, beta, or gamma, or any value, if you take, the set that you are getting has to be convex. So here you can find that all these sets are convex, right? All these sets are convex. Yeah, so that is the definition of convex set. So if you take another example, f of x is root of absolute value of x. So which will have a shape like this. Root x has a shape like this. So we cannot define that for minus x, right? So we just take absolute value. So that will have a that will add a symmetric part here. So this is uh, root of absolute value of x. So if you consider any alpha here, for example alpha 2, which will have a sublevel set this guy, alpha 1, which will have a sublevel set this guy. So if you take any alpha, that will have, you will get a sublevel set which is convex. So this function is a quasi-convex function. So that's what the beauty of this function. Such function we can actually minimize by some means. Okay. Yeah. So that is one thing. Another thing is when do you say a function is quasi-concave, right? It's like a definition of concave function. Like when the minus f is convex, we can say that it is concave, right? So similarly, minus f is quasi-convex, then we can say that the function is minus f is quasi-convex, then we can say that function is quasi-concave. Or we can also use alpha super level set. What will be the super level set? Here, yeah, for example, sublevel set is, how do you form a sublevel set? You take any alpha as alpha 1, okay? Sublevel set corresponding to alpha 1 will be all the value of argument where the function take value less than alpha 1. So super level will be the opposite of that. So for example, if you take this function, this is quasi concave function where if you take any super level set, alpha, so super level set will be uh, the value of argument x. So this is x, function of x. So value of argument for which the function take values greater than alpha. So that will be this guy here. So this is alpha super level set. So one way to say convexity, quasi-concave, one way to define quasi-concave function is minus of that function has to be quasi-convex. The other way is you can say that all the super level set has to be convex. Okay, both are equivalent. Now another thing is, what is a quasi-linear function? That's simple when the function is both quasi-convex and quasi-concave. Okay, so some functions are like that will be both quasi-convex and quasi-concave. Can you like guess an example?
absolute x.
Absolute of x.
No, no, that's
That's not right.
no, that's just connect.
Absolute of x is a convex function.
Yeah, something like.
Okay, so one thing is this class is like more general. So convex function is like more strict. So what I'm saying is you have a class of quasi-convex function. Okay, so this is more relaxed.
Yeah.
And then our class of convex function is inside this. Okay.
Yeah.
Right.
So we're looking for one that is quasi-convex and not convex.
Sorry, what is your point?
Now we're looking for a function that's quasi-convex, quasi-concave.
Yes. So yeah.
And
So
quasi-linear.
yeah. So now I'm asking, can you guess a function which is quasi-concave and quasi-convex both? Sin x. No, how can that be? Let's draw. Sin x is neither quasi-convex nor quasi-concave, right? Because if you draw, for example, alpha sublevel set, it will have a non-convex domain, right? It will have different discrete parts, right? What I mean that, for example, if you consider super level set, it will be this guy, this guy, this guy, something like that. So that's not that doesn't fall into both of this category. Yeah. So one simple example will be a linear function, right? Which will be both quasi-convex and quasi-concave.
And convex.
Yes. Yeah. So maybe that is not a good example. Yeah, because that's already. So yeah, I agree. That's not a good example, but that's again fall into this category. The point is, for a function to be quasi-linear, it doesn't need to be linear. That's the one thing. It is far away from the concept of linearity. We just use the word quasi-linear, but it has nothing to do with linear functions. Okay, but linear function of course falls into this category also. So let's see some of example. So one of this quasi-linear function is log x. So let's see what it is. So this is log x. Okay. So now that what we have to see is all super level set and sub level set has to be convex. So if you consider alpha, okay, what will be the sub level set? It will be this guy, right? This guy, right? This blue one, right? What will be the super level set? This guy. So both are convex. So if you pick any alpha, you will get sub and super level set to be convex. So this guy log x is a quasi-linear function. Yeah, so let's see some of the example. One is root of absolute value of x that we already saw here, which is a quasi-convex function. Another function is ceil of x. What is ceil of x? It is what to say, next greatest integer. Next smallest integer. So you have 1.2, ceil of x will be 2. Okay, you have 5.3, ceil of x will be 6. I'm correct, right?
Yeah.
The floor is the floor of 5.4 will be 5, right? So that will have a ceil have a shape like this. This is the ceil function. So you can see that both its alpha sub-level set and super level set will be convex.
What about sin x minus pi by 2 to pi by 2?
So you want to, so what will be the sin x? Minus pi by 2, it will be having value 1. Okay. Then
minus 1 to plus 1. Minus pi by 2 to pi by 2.
So this guy?
No, it will be like
a smooth stair, I think.
Minus, sorry, repeat again.
Minus pi by 2 to pi by 2. So it will be minus 1 to plus 1.
Minus pi by 2 to something like this. right? Yes, it looks like a quasi-linear. If you yes, if you consider any alpha, yeah, it looks like quasi-linear. Okay, and yeah, so what? Well, yeah, seal function. Then this guy, if you take sub-level or super-level set, that will be, for example, at this point, uh, sub-level set corresponding to one will be this part, and super-level corresponding to one will be this part, which is both are convex. So we can say that this guy is quasi-linear. And log x, we already saw what it is. It's a quasi-linear function. And now another thing is f of x, x1, x2 equal to the product of x1 and x2 on R plus plus, means 0 is excluded. Yeah, so let's see what it is, this guy. So it is saying that is quasi-concave. Yeah, so you can see this is my function. My function is defined like this. So let's consider the super level set of S alpha super level set. So let's pick two elements, two vectors, x belonging to super level set and y belonging to super level set. What does that mean? X1, x2 is greater than alpha, right? Why greater than alpha? Because we are considering super level set, okay? And y1, y2 greater than again alpha, right? So are you following? I'm picking two elements from the super level set, okay? That means the argument, the function value has to be greater than alpha, okay? Now what I want to observe is whether this set, super level set, is convex or not, right? So we have two elements from that set. How do you say whether it's convex or not? How do you check? Take the convex combination and see whether that belongs to the set. So what is a convex combination? This guy, right? You know that. Yeah, of course theta has to be in between 0 and 1. Yeah. Now, so how do you check whether this guy belongs to the set, sub-level set? So take the function value from this vector, that is multiply the first argument and second argument and check whether that is greater than alpha. So what is the first element of this guy? Theta x1 plus 1 minus theta y1, and same, right? Theta x2 plus 1 minus theta y2. Multiply it together, you will get this guy here. Now, yeah, to prove this, you will make a small multiplicative adjustment here. Here I am just multiplying with x2 and dividing by x2, okay? So similarly here. So now we can apply this inequality here. So we have x1, x2 here. So x1, x2 here, I can replace this with an inequality alpha, right? I am replacing x1, x2 with alpha. And I know that that will be greater, lesser, right? When you put alpha instead of x1 and x2, you can use this inequality. Alpha. Here also I am replacing that with this y1, y2 with alpha. Here we have x2, y2, x1, y2. I am replacing them with alpha and taking alpha outside. Now, on the next step, I do a small adjustment where I write this guy as root x1 by x2 minus root x2 by x1 whole square plus 2. You can just verify this will be same. Yes. Now this is a positive quantity. Okay, I can drop that again using equality. I drop this positive quantity and just take this 2. Okay, now I have this guy. So since I'm dropping, I'm using this inequality here. Yeah, so this guy here, if you like take alpha common, it will be theta plus 1 minus theta whole square. That will be alpha itself. Okay, so what we proved is that product of this guy and this guy is greater than alpha. So that means that is belonging to the super level set. That means this super level set is convex, which means our original function, this guy, is quasi-concave. Okay, that's what we prove. Of course, if you just see this function, we have f of we have this function f of x, the f of x x1 x2 equal to x1 plus x2. If you take the gradient and then take the second uh, uh, take the Hessian matrix, you will get this guy whose eigenvalue will be -1 and +1. So this is neither convex or not concave, but this is quasi concave. Okay, so this is how we prove. Is this part of the homework?
I don't know.
Okay, so you have not started. I'm not sure. If this is the part, I think I gave you a free answer. Yeah, so that's this guy. Another guy is linear fraction function. Next is distance ratio. Just have a quick look. So linear fraction function, which will be having this form. So that is both quasi-convex and quasi-concave. So let's consider one case, alpha sublevel set. So we have to say that the function value f of x is less than or equal to alpha, right? So then pick all those x. That is the alpha sublevel set. So x such that first condition is the domain constraint should be satisfied. C transpose x plus d has to be positive. Second, this is the definition. This is coming from the definition of the function. Second, we are considering alpha sublevel set, so we have to say that the function is less than or equal to alpha. So then we can write this guy from this definition. So what is this? If you rearrange slightly, you can come up with this form. So this is the intersection of half spaces, right? So this is one half space, this is another half space. So this is the intersection of half spaces. So then that's a convex set. So this is an open half space, this is a closed half space, right? And so this is convex. Now, if you take this is sub-level set. If you consider a super level set, what it will be? Again, it will be similar. Instead of this less than or equal to, you have to write greater than or equal to alpha. So you will again get something similar. Only difference is here you will be having greater than or equal to sign. Again, that will be intersection of some open half spaces and closed half spaces, which will be convex set, right? Clear? Another example is from here, distance ratio. So you have this f of x, which is x minus a norm second norm divided by x minus b second norm, which is the Euclidean norm. So here we are considering again. Let's form the alpha sublevel set, which is formed by considering equating this or putting this inequality. This is less than alpha. Okay, less than alpha. So you will get this. So, but here the point is, I think in the definition. So this function is defined such that domain of f is defined like this: x such that x minus a norm of x minus a is less than or equal to norm of x minus b. That means we are saying that this distance is less than this guy. That means we are saying that this will be the value of this fraction will be less than or equal to 1. Okay, that is the definition of this function. Okay, no, don't worry, we are just taking some crazy function and examining its quasi convexity. Okay, so this is, we just define a function like this, and now we are just checking it whether it's quasi concave, quasi convex or not. Okay,
But if it is both quasi-concave and quasi-concave, what is the name of that function? Yeah, in general.
that is quasi linear.
Quasi-linear.
Yeah, that's what we,
Quasi-linear is not technical.
okay, that is quasi-linear. So we saw some quasi-linear. One is the seal function, other one is log x, right? Yeah, yeah. This one is also quasi-linear, and now we are checking this one. But here we put a strange constraint here in the definition of the function, where this guy has to be less than 1. Okay. So in that case, now what you have to do is, let's consider the sublevel set. This is less than or equal to alpha, which gives this guy. If you rearrange, just take squaring both side and rearranging, you will get something like this. Now you can check this later. Maybe you have to rearrange this and say like see that it's a Euclidean ball. Maybe you can check this. What will be the center of this center and radius of this Euclidean ball? Okay. For that you have to slightly rearrange the terms here. Yeah, and see. So that's a Euclidean ball. That will also be which is a Euclidean ball is a convex set, right? So that will be convex. But this will be Euclidean ball only for alpha is less than or equal to 1. Okay. So then you cannot consider this for a say like here we had the same convexity for both sub and super level set, but here that you can verify that it will be held only for sub level set. So that is quasi convex, not quasi concave. Yeah. So to see that, you just need to like rearrange this and see what is the radius and center of this, and just try that for alpha is greater than 1. Then you will fail to get a Euclidean ball. That's okay. Yeah, so maybe let's take a small break here. Okay. Yeah, now we saw what is a quasi-concave, quasi-convex, and quasi-linear functions. Let's see whether I missed something. Yes. And now there is an example from finance. I will cover this at the end of the lecture, okay? Towards the end. Let's skip this as of now, because the moment you start, you may ask a lot of questions, a lot of discussion may goes on. So let's keep that towards the end. I don't want to spend a lot of time on that. So let's move to the next topic. Yeah, so for not next topic, the continuation of this. So for a quasi-convex function, yeah, we can again use the Jensen inequality in a slightly modified way. So what was the Jensen inequality? So we, in a convex function, this guy has to be less than or equal to theta f of x, converse combination of those functions, right? F of y. This is what the Jensen's inequality, right? Yeah, so we know the normal Jensen's inequality. Here, for quasi-convex function, of course, that usual Jensen's inequality will not be held, right? So what we do is we go for a modified version of that inequality. So we have a quasi-convex function here. So instead of saying this line, so we have 2 point x1 to x1 and x2. So instead of saying this line lies above the graph, which is not happening here, right, for quasi-convex function. So now we say that this line will be less than maximum of these two guys. So you take maximum between f of x1 and f of x2, which is f of x2, right? So now I say that this line is less than the maximum. This is how we define quasi-convexity using Jensen's inequality. So this is another way of defining quasi-convexity. What was the first way? We defined as using sublevel set, right? So here is the second definition, using modified inequality, which says that you have 2 points x and y, and the function evaluated at any points between x and y will be having a value less than maximum of f of x and f of y. That means even if you consider any point in between and evaluate the function, okay, that will have a value less than maximum of these 2 points. Okay, that's how we define quasi-convexity. Another Yes. Another useful concept is the first order condition. So let's see what it is. We have a differentiable function here with convex domain, and it is quasi-convex if and only if f of y. So let's say this is a this is a level set of the function, It's like the contour. That means, uh, so maybe this is the optimum point, minimum point x0. At that point, function takes minimum value. So if you keeps on increasing, like going away from x0, you will have a higher value of the function. So you understood what I'm saying, right? This is the like contour plots. That's it. Yeah. Okay. All of are okay with that, right? So basically means if I go this direction, I will go to like the value of function decreases. It's like something like this. Okay. So let's say we are at this point x. Okay. And now I can say that f of y is less than f of x. That means f of y will be, so this is the contour where the function has the value f of x, right? So now I'm saying that f of y is less than that. So that means f of y can be anywhere here, right? So I can say that like f of y is less than f of x, which implies this inequality holds. How it is coming? It is coming from the definition. We know what is the equation of a like a tangent or hyperplane here, right? This is the equation. From this, if you consider f of y minus f of x, then if you take that is less than or equal to 0, then you can equivalently define this, right? So now the interesting point is, what does this mean? This is the equation of a half space, which says that, so you are at this point, which says that you have to go towards, so half space is, this is defining, right? You can just rearrange this and write like delta transpose y minus delta transpose equal to delta transpose x. And yeah, so that says that, okay, you have to go, this is in this direction. So this equation is defining this half space, okay? This is useful in later when you study, for example, gradient descent algorithm and other iterative algorithm, where if you are at this point and you want to minimize the function, or if you know the gradient at that function, you can find uh, the direction which you have to go to minimize the function. Now, what is this telling is, you do not need to go to this direction. You just need to go this direction. So this is giving you an information whether it's left or right. You have to travel to minimize your function. So it's like a giving you one bit of information, right? Left or right, one bit of information. So that's an important property of quasi-convex function. Okay. Yeah, so of course for convex function also this will be, you can apply this. Yeah. Now, uh, yes, that is the first order condition. Let's move to another concept, which is log concave and log convex function. These are again symbol definition. A positive function f is log concave if log of f is concave. Okay. Or for example, you have a function f, you take log of that. So log of f is convex. Okay. In that case, you will say that log that function f is log convex. That's all. Okay. Here I am defining. Usually we everything we define with respect to convexity, right? Quasi-convex. And here we are mentioning log concave function because that's the that comes most often in our research. For example, if you take a probability density function or a cumulative distribution function, most of the things are log concave. That's why we define using we give definition for log concave functions, not convex. But we can have the similar definition for log convex function also. So what is it? The function of is log concave. If you take log of the function, that should be a concave function. So how do you say that? So how do you get this? So this is simple, that this definition. So if it's log concave, if it satisfies this inequality. So just see this derivation. So what you are saying is the log of the function is concave. So you can write this inequality, right? Log f of theta plus 1 minus theta equal to 1 theta into log f of x plus 1 minus theta into log f of y. Now just here isotem, take this theta to the exponent. Now we have sum of two log, which will be multiplication of two log, right? You have log both sides, like cancel those logs, then you will get this definition. Okay, so this is for concave log concave function. You can derive a similar definition with a reverse inequality for log convex function also.
So is fx is x, like just the line. Is that log concave? Because I
Fx,
think the log of x is
yeah,
concave.
yeah. So fx is x, right?
Yeah.
So now you to check whether it's log concave or convex, just take the log of that. So log x.
Yeah.
Okay. So log x is
Concave.
concave. So
X.
f is x is
Log
yeah,
concave.
yes. Yeah. So here are some example. Uh, power of x. Yeah, this is something. This is what you said. Power of x. So this is f of x is x raised to a, right? So when you take log f of x, it will be a into log of x. So if a is positive, this will be uh, concave. A is negative, this will be convex. Okay. In your example, it was 1.
Yeah.
Yeah. Another function is uh, like probability density function. So many probability PDF functions are log concave. So here is one example. F of x. So this is the Gaussian or normal PDF, right? Which has this form. I hope all are familiar with this. So yeah, so if you take the log of this, what will happen? So this is like a constant k into exponential this guy here over here, right? If you take log of this, it will be log k plus log of exponential of this guy. So basically, you will get this thing, right? If you take log of that. So is this a convex or concave function? My question is minus half x minus. Is this concave or convex?
It's concave.
This is which function? It's a quadratic function, right? Yeah. So it depends on. Okay, just remove the minus. What is remaining? That is, let's take.
The sigma inverse.
Yeah. So if I say that sigma I inverse is positive definite or positive semi-definite, then what will be this function? I am
That
giving.
is convex.
This is convex, right?
Yeah.
Yeah. So like here, this is a sigma is a covariance. Sigma is a covariance matrix, and this will be the inverse of that. Okay. So covariance matrices are positive semi-definite. Okay. So let's don't complicate. Let's say that this is positive definite. It inverse exists, and so in that case, uh, this is called a well-conditioned matrix. Yeah. So this is a positive definite. Let's consider like that. In that case, this will be uh, convex. And if you put a minus sign here, this will be concave. So that means when you take log of this function, you are getting a concave function. That means this function is log concave. So you can just verify this for other densities that you know. For example, exponential or chi-square density. You will also see that they are log concave function. Okay, just check that. Now another thing is a cumulative distributive function, which is the integration of PDF, right? So we have a function here. So this is very difficult to see, but we are not going through the proof. We just mentioned. So here we have a CDF function for uh, uh, Gaussian normal distribution. So I hope you know what is this CDF. So at any point x, So this is a PDF here, probability distribution function. So at any point x, if you want to find the probability up to that point, what you do is integrate from minus infinity to that point. Right? You consider this area. That is what this is doing. So this function is also log concave. So yeah, so this is not only for a Gaussian function, it's applicable to all other PDF. Okay, so you are integrating and that will be log
Because
concave.
now the increase after one.
I don't know.
It's like how do you call it? Increasing, it's an increasing function.
Q function is like the
Q
final-
function is 1 minus of this, right?
Yeah.
Yeah.
I don't know
But
the,
if you just integrate an area,
yeah,
it can only like it's like this sine function. It's
yeah,
still,
it will increase like this. Yeah,
Yes.
that's one way of saying it, but I don't know the formal proof. Okay. Yeah, but intuitively it's like that.
it goes from
Yeah,
0 to 1.
yeah. It will be like this and then rising.
Yeah.
And, yeah. So after this domain, it will take value 1, right?
Yeah.
Constant. Yeah. 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 So some properties of low concave function. One is so let's see. Yeah. One is if the function is twice differentiable, we have this expression here. So how do you prove that? So let's say g of x, let's consider a function g of x, which is log of f of x. Now I am taking the derivative here. You will get this Hessian here. You will get this. Now what I'm saying is this is log concave. That means this guy has to be less than, this is Hessian, right? Second order derivative. So that should be less than or equal to 0. So that, so remember that these are generalized inequality, matrix inequality, okay? So this will be less than or equal to 0. That means just take rearrange the terms, we can say this, okay? So that's what this property. So if the function is log concave, then this will satisfy. Now next is product of log concave function is log concave. So you have two functions, f1, f2. Let's assume that they are log concave. That means log of f1 and log of f2 are concave function, right? Now let's make a new function g equal to f1 and f1 into f2, product of those. So what will be log g? It will be log of f1 and log of f2. These two are concave function that we already saw here. So then sum of concave functions are concave. That means log g is concave, means g is log concave. Okay, so it's simple proof. Now you can see this sum of, usually when you take sum of two convex function or concave function, that will be convex, right? But here that is not always true. So I for further reading, you may read properties of log concave function. Yeah. So again, another property which we are not going to prove, which is difficult. So you have a function f in x and y, which is log concave. Then you can integrate the function over one variable, and that certain function in x will be log concave. So since he is expressly saying not easy to say sure, I didn't go to check for the proof. Okay, just let's skip. So some consequence, yeah. One is like we'll just rush through these topics. One is convolution. So what is the convolution between two functions? It will be, this is the basic convolution formula. So you can see that this is, if you assume that f and g are convex, so this is a, sorry. If you assume that f and g are log concave, so this is one log concave function in x and y, another one, another log concave function, product of that which is log concave. Then we saw that from the integration property, that will also be log concave. So when you take a convolution between two log concave functions, the resulting function will be log concave. And another thing is you have a probability. You have a set C, which is convex, and y is a random variable with a log concave PDF. So for example, y has a Gaussian PDF, okay, a normal PDF. In that case, this probability, how do you define this function? This function is such that the probability that x plus y, the function evaluated at value x is such that it gives the probability that x plus y belongs to this convex set C. So how do you write write the probability? You just integrate with respect to PDF, right? Now we are saying that this is a this PDF is log concave. Then we can write this when x plus y belongs to C. I am forming a function g such that when x plus y belongs to C, that g will take a value of 1. If it doesn't belongs to C, it will be 0. So basically that will integrate the probability, that will integrate to get this probability that y plus C belongs to C. It will integrate over this domain if you define the function like this. Anyway, this is also log concave because you have two functions here, which is log concave. Then it follows from the property of integration. Okay, so let's just skip these topics. Again, there is an example. We will skip this yield function. So you can just go through this. I don't know in detail what is this function doing. It's from some application, manufacturing application or something, but it will be having a same form like what we just saw here. Okay, so we can write that as an integration, and again that we can prove that that is it's same as what we discussed here. Again, we can prove that that is a log concave function. Yeah. So let's go move to another topic, which is an important one. Convexity with respect to generalized inequality. So yeah, so far we defined convexity for functions, an objective function having this form, right? Right. Now what happens if you take an objective function from Rn to Rm? So now your objective function is not a value in R, it is a vector itself. Okay. So in that case, how do you define convexity? Okay. So of course, then the picture, that is the concept that is coming to your mind should be a cone, right? We saw how can you compare or define inequality for vectors and inequality for matrices, right? So for vectors, we use the famous inequality is using a proper cone R plus, right? R, Rn plus, which is a component-wise inequality that we saw. For matrix, we can use an inequality, define an inequality using positive semi-definite cone. Right? These are two inequality what we learned, which are famous, right? So now we use similar inequality here, generalized inequality, and plug that in the definition of convexity. Yeah. So how do you compare this? So now just consider the, for example, if f is mapping from Rn to R, we had the normal inequality, Jensen's inequality for convexity. Now what we are seeing that it's not for Rn to R, it is mapping to a vector Rn. So now these f is a vector now. F gives you a vector. So how do you then define the inequality? Using a cone. It's not a normal cone, it has to be a proper cone, right? Okay, so here I am defining this using a inequality with respect to k. So like this we can define convexity. Okay, so now for vectors, function maps from vector to vector, we define Jensen's inequality using a generalized inequality associated with a proper cone. Here is an example. A function which is mapping from symmetric matrix to symmetric matrix, which is given by f of x equal to x square. So x into x. Okay. And this is okay. So if this is satisfied, then we call this as k convex. Okay. So it's not convex, it is convex with respect to the proper cone k. So then we say that this function is k convex. Now, yeah, so now we will prove that this function, which is f of x equal to x square, is convex with respect to this cone Sm plus, which is a positive semi-definite cone, right? How do you prove that? Okay, so this is the function that we have. Now we have to prove this. The proof is here. So let's consider another function h of x, which is given by z transpose x square z. Okay, this I can write as x of z norm Euclidean norm square. Why? Because this is equal to z transpose x x square is x z, right? Now since this is symmetric, we are assuming that x belong to the symmetric matrix. Since that is symmetric, I can replace this guy with a t here. Okay. Now I can write this as x of z transpose into x of z. Okay, which is this guy. Yeah. So let's consider this function, new function h of x, which is given us like this. So is this convex in matrix X? The variable is capital X here. Is this convex? See, this is, you don't need to complicate, just consider this as a variable, okay? X. Now, what you are having is just multiplying that with a vector. So it's an affine function in X, right? Or a linear function, more specifically. Linear function in X. You are taking the norm of that, okay? So linear function is a convex and you are taking the norm of that. So the overall function will be convex. So this guy is convex. So since it is convex, we can write this definition. So what I'm saying that H is convex in X. So I just took 2 points, X and Y belongs to the same domain. And I'm writing this inequality, basic inequality of convexity. Yeah, so what is H? I just plug in that here. H is Z transpose X square Z. So Z transpose this guy whole square into Z equal to theta into H of X. Again, I use the formula of H. Here I use the formula of Y. Now just bring all terms to the left side or right side, to the right side. Yeah, and take Z outside. Here I take Z transpose to left and Z to the right outside. Now what you are having is this guy. Now what I'm saying is this guy is greater than or equal to 0. Okay, that means you have a quadratic expression here. I'm saying that that is taking a value greater than or equal to 0. So at this point, until this point, you just have a scalar number, right? So what is this? This is a quadratic form which give a real value. Okay, this is not a vector. This is a number, a real value. So now what I'm saying is that number is greater than or equal to 0. That means this matrix has to be positive semi-definite. So this matrix, which is this guy, has to be positive semi-definite. Now we can just rearrange the terms and write like this. So here you know that. So this is here. This is like your f of x is x square, right? Square, square. So your f of x is x square here. So here you can say that this function of x square is, this inequality is satisfied with respect to this cone. So S plus convex. Okay. So that's one example for K convexity. Fine. So we have 10 minutes. Let's move to the example that we skip. Internal rate of return. So this is a concept, an example from finance. Where let's say we are considering cash flows here. Let's say we are starting a project, okay, at zeroth year. Okay, these are years, zero, first year, second year, third year, okay, the timeline. So when you start the business or a project, you invest, for example, $10,000, okay. So that's why I am writing this as minus 10,000. Okay, that is the money that is went out of your pocket. So minus 10,000. So let's say at first year you got 2,000 return, second year 3,000, and third year maybe 1,000, something like that. So now what actually we need to have is when you sum all this has to be positive, right? Then only you will get a return, right? This your 10,000 is this x0 that you spent initially, and these are your returns here. So when you sum all of these, at least you have to get that to be positive, right? Otherwise you are in a loss. So this is a we assume this, but this is a very weak assumption, because there are many concepts like mm, inflation, interest, and there are many things in finance, right? But this doesn't take care of that. So one thing is interest. So a money, for example, a 10,000 euro after 5 years, okay, is not same as the 10,000 euro at present, right? Right? It will be for example, if you put 10,000 euro in bank today, after 5 years, that you will get the interest corresponding to interest that will vary. So you cannot compare just money like this. So you have to plug in this interest factor there. So let's take an interest. So how do you so after accounting this interest, how do you uh, uh, from the net value? That's a question. So what we do is when we take sum, okay, first year. So what I'm seeing is when I start project at this point, the present is at this point, okay. Now I am converting all the money to the present instant. I'm considering, I'm checking the value of money at the present instant. So you will have some expected return. So I'm going to start the business. So I expect that after the end of first year, I may get this return because of I have some criteria to evaluate that expected value. Based on that, I expect that okay, by the end of first year, I will get 2,000, then 3,000, and then 1,000, something like that. So the net value at present is calculated like so this I already spent plus, so 2,000 is the money that I am getting after 1 year. So what will be the present value of that money? This will be divided by 1 plus r, right? R is the interest rate. For example, if you are having an interest rate of 8%, okay, so if you put a money for example, if you put a money x in bank now, after 1 year you will get how much? X into 1.08, right? Right. So for example, this was your money after 1 year. To get the percent value, you have to divide this with 1.08, right? That is this 1 plus r here. It's the interest plus 1, right? Now the next quantity is 3,000. So I have to divide this guy by, so 2 year interest, right? So it will be square. It will goes like this. That is this formula over here. So you don't need to divide with the initial value because you are calculating your percent is at this point at zeroth year, so you don't have a time gap there to calculate the interest, so that you can consider as it is. So here when you put I equal to 0, you will get just x 0. So this is the present value. This is called present value of cash flow. Okay. Now this is just an example. Okay, from finance. Now internal rate of return is the, so now I calculate this value, and now let's assume that if the interest is high, what will happen to this? As the interest keeps on increasing, this factor will take a small value, right? Right? And then your net value tends to be negative if you increase a lot. But if you decrease the interest, right, the net value will increase, right? Now what I'm saying is, at what value of interest this net return is becoming 0. So because 0 is a crucial point. If I go to negative, I am in loss. If I go to positive, then I'm good at this my business. So so that is the important thing here. So I am interested in seeing what value of rate, interest rate, this guy is 0. So so that is called internal rate of return. But it is not only a particular value of rate, it is the minimum of that, because this is a polynomial, and when you take when you equate this to 0, you this is a polynomial in a higher order, so you can have different values of interest which gives you 0. So you consider all those interests and take the minimum, so infimum of all those values. Okay, so this is called internal rate of return. And uh, now this is a very complicated function, you cannot visualize this, but the good thing is, if you consider a super level set of this, okay, you will get uh, an inequality like this, which says that this is your percent value, this has to be positive. So what you are saying is the super level set is greater than R, which means that you are finding all the possible set, means it is the point of collection of X, right? So you are finding all the collection, or all the possible cash flows for which the smallest interest rate of 0% value is greater than R. That is what this is mean. That means IRR X should be greater than R. Okay, so that again means this you can equivalently say as, so within the value in the, when the interest is between 0 to R, your this value is positive. Okay, if you increase further the interest, that will this net value will goes to negative. Okay, so this is what this an equivalent definition of this sub-level set, oh, sorry, super level set. So this again we can see that this is simply half space. Okay, so just like this is just an example from finance, but the good thing is the what we are trying to say here is this was a complicated problem, but then later we saw that the super level set of that problem is uh, uh, containing half spaces, intersection of half spaces, then they are convex. That means our original problem is quasi-concave. Okay, so at least we have now the hope that, okay, this is quasi-concave, now we can maximize this function. Okay, so this is just an example, but if you are it's you can just see, try to understand this, but in case if you are not comfortable, you can just skip this, no problem. Yeah.
We found that the intersection of obvious is convex. Then, then you reached quasi-concave. So I didn't understand that.
Yeah, because we were considering the super level set here, not sub level set. So if the sub level set is convex, then it is quasi-convex. If the super level set is convex, it is quasi-concave. That's what we saw, right? For example, this guy is quasi-convex because sub-level set. This is convex, but this guy is quasi-convex because then we have to find the super level set. This is convex. Yeah, so let's stop here.